Hello everyone, I'm Yili. I'm here to present my work, LiquidSense. It's a joint work done with my advisor Professor Yang and other group members. First, I'd like to introduce the background of Wi-Fi applications in a smart home, especially the liquid level sensing. In recent years, Wi-Fi is becoming more and more integrated into our daily life. For example, the Wi-Fi can connect with a smart refrigerator, smart light, voice control system, and smart container to a smart device via Wi-Fi network. Among those emerging services, sensing liquid level has gained increasing attention because liquid sensing provides the information of when and how much the liquid content has been consumed each day. It can help us to estimate and track the calories ingested, help patients to manage medicines, and provide expiration notification and even automatic reordering. There are some research works in liquid level sensing. In general, the approaches can be divided into four categories. First, capacitive-based approach. The capacitance sensor has very good sensitivities, but uh, they usually require the sensor to be immersed into the liquid. Second, the camera-based. It could capture many containers at the same time, but it only works for transparent containers and suffers from non-emphasized or poor scenarios. Next is using pressure sensors. High accuracy can be achieved, but this system requires containers to have flat bottom and need calibration. Last is acoustic based. It requires the specialized acoustic hardware to acquire the accurate measurement. In addition, all the above-mentioned approaches all require additional communication hardware for each container. Now I will introduce our solution, LiquidSense, a new approach for liquid level sensing. The basic idea is as follows. We reuse the existing home Wi-Fi network to sense the resonance frequency of the container liquid system for liquid level detection. Our system reuses a low-cost transducer attached to the container surface to generate a vibration. The well-designed vibration allows the container to have a high-frequency micro vibration at its resonance frequencies. Such micro-vibrations will introduce subtle changes to Wi-Fi signals. Through detecting the subtle changes in Wi-Fi signals, LiquidSense extracts the resonance frequency of the container for liquid level detection. Now I will discuss why Wi-Fi signals can sense micro-vibration of a container. Assuming we have a transmitter and a receiver, we put the container at a proper distance and the container is vibrating. Because of the vibration, there will be a small displacement on the surface. When the displacement is changing, the reflect path of Wi-Fi is also changing. In particular, it changes from path P to path P hat. When path P becomes path P hat, the path length increases and the signal amplitude decreases. As long as the signal propagates one wavelength, the phase changes by 2 pi, so the phase will also change. So we can conclude that both amplitude and phase of Wi-Fi can indicate how the signal paths are changed by the vibration. Channel state information describe how Wi-Fi signals are changed in the physical space. So changes in amplitude and phase of CSI for each OFDM subcarrier indicates the change in amplitude and phase of Wi-Fi signals. But for our system, we focus on analyzing the phase component. This is because phase offset is more sensitive to subtle vibrations. To better capture the feature, we adopt the PCA by combining all the subcarriers' phase information. We select the first principal component. In order to extract the accurate resonance frequency, we need to conduct SDFT on the first principal component. We can see both the first and the second resonance frequency, but the first one is much stronger. We select the first resonance frequency as the feature. Now we are going to build two models. One is continuous and another one is discrete. For continuous prediction, we adopt curve fitting. To achieve best curve fitting, we adopt piecewise polynomial interpolation and cubic polynomial. For discrete prediction, we adopt SVM with linear function kernel. We conduct experiments with two laptops. One is the receiver and another one is transmitter. We use 5G Wi-Fi and the packet rate is 2000. We connect the transducer to the control board to adjust the transducer. We chose 4 commonly used containers in daily life. They are made up of metal, glass, and ceramic. The experiments are conducted in a typical home environment with 6 types of liquids. Now we show the overall performance of the 4 continuous model. The first figure shows the CDF of error. We can observe that 90% of the error are less than 6%. In the second figure, the overall accuracy is greater than 97%. This shows our system is highly accurate in continuous manner. Our system also performs well in discrete manner. In particular, our system can achieve better performance at high liquid levels, and the overall precision recall and F scores are larger than 0.96. All in all, we propose a novel liquid level sensing system. Thank you for listening.